Now I just want to spell out quickly what happens if we subdivide more than once. First we use this notation, all right, k bracket 0 for k itself, and k bracket 1 for k dashed, k bracket 2 for k double dashed, and so on. Same kind of notation as for derivatives of a function. Then we're going to define this beta bracket I, right? So we start by taking the map beta from k prime to k, from the realization of k prime to realization of k, and then we also have a map beta from k realization of k double dash to realization of k dashed, and so on. And we're composing all these together. We get a map from the realization of k to the I to the realization of k. That's what we're going to call beta bracket I. And each of these betas here is a homeomorphism, so the composite is also a homeomorphism. Next, we have this map mu from k dash to k, last vertex map. Does rely on choosing an order of the vertices in k. Then once you've chosen an order of the vertices in k, well, it's not hard to spell out order on the vertices of k prime if you want, or you can just choose one randomly. Anyway, so then you get further maps mu from k double prime down to k prime, k triple prime to k double prime, and so on. Composing all these together, you get a simplicial map from k bracket I all the way down to k. And so then we proved various things about the beta and mu before, and then we can extend these by an obvious kind of induction to prove things about k bracket I, beta bracket I, and mu bracket I. Firstly, you've got this map beta bracket I from the realization of k bracket I down to k, so it's meaningful to talk about a simplicial, direct simplicial approximation to that, which should be a simplicial map from k bracket I down to k, which is the same kind of thing as mu bracket I, and easy inductive argument shows that mu bracket I is indeed a direct simplicial approximation for beta bracket I. We proved that before for the case I equals 1, and then we also proved a thing about direct simplicial approximation is compatible with composition, and using that we find that mu bracket I is the DSA for beta bracket I. Similarly, we know that mod mu is homotopic to beta, so each of the maps called beta here is homotopic to the geometric realization of the corresponding mu and in this line down here, and homotopy also respects composition, so a realization of mu bracket I is homotopic to beta bracket I, and and then each of the bracket realization of mu's is homotopy equivalent, so when we take composite, that's also a homotopy equivalence. Similarly, each of these mu's gives an isomorphism in homology, so their composite also gives an isomorphism from the homology of k bracket I down to the homology of k. And finally, each time we compose with beta, well, assuming the dimension is less than or equal to d, each time we compose with beta, we reduce the mesh of any map by a factor of d over d plus 1. And so we do it I times, then the mesh of f composed with beta bracket I is at most d over d plus 1 to the power I times the mesh of the original map f.